Let's look at another type of series parallel circuit. Now, in this case, we actually have three sources. And you're probably not used to seeing multiple sources in your circuit if they're not in series, and these are not. Also, if you notice, none of our resistors are in series or parallel, so we can't use the reduce and return method here. We can't reduce these down. So we're going to have to use some other tools in our toolbox. So what tools do you have so far? You've got your Ohm's law. Whoops. Ohm's law, right? We have KVL, KCL, we have the voltage divider rule and the current divider rule. So these are all tools you can use in your circuit analysis. We're going to focus on, this time, KVL and KCL. Remember, Kirchhoff's voltage law tells us that the sum of the voltage rises around a loop equals the sum of the voltage drops around the loop. Okay, and KCL says the sum of currents entering a node equals the sum of the currents leaving the node. So we're going to use those two relationships a good bit here in this problem. So how do we do that? Well, we identify different loops we can use for our current voltage, Kirchhoff's voltage law equations. So we could use this loop in here. It kind of looks like that. There's a loop in here we could use. There's a loop here we could use. We could go around the whole circuit. So there's a few different opportunities for us to write voltage law equations here. So it doesn't really matter where we start as long as we start in a place where we don't have too many unknowns, okay? So for instance, I'm going to remove this because two of those three voltages in that group we don't know. We only know the one that's that source E2. And two of our drops here we don't know. Now notice either of these next two, we actually do have just one unknown voltage. For instance, if we look at this particular loop right here, we know our voltage here, we know our voltage here. The only place we don't know the voltage in that loop is here at R3. So we could write an equation there. For our second loop out here, again, we know E1 and we know E3 over here. What we don't know for this loop is our 10 ohm, whatever that voltage drop would be. So let's just start with the first one. And what I'm going to do is I'm going to name this voltage V3 because we don't know what it is. So I'm just going to name that voltage there. And I'm going to write my KVL equation for loop 1. So I'm going to start here and travel around the loop this way. And we see that we come to a voltage rise of 20. So I'm going to call that plus 20, right? From negative to positive is a voltage rise. And then I'm going to continue around my loop until I get to E2. And I see that that's going to be in that direction a voltage drop. We're going from plus to minus. So minus 5 volts there. And continue on this way. Now, we don't know if this is a voltage rise or a drop, so I'm just going to make an assumption. I picked plus to minus, and I'm assuming it's a drop. If it's not, my equation will help me figure that out. Okay, so, and then I continue on, and when I get back to where I started, that prompts me to set everything equal to 0 because I've completed that whole loop. So now when I solve for V3, if I move V3 to the other side, it becomes positive, and I see that V3 must be 15 volts for KVL to work, right? So this would have to be 15 volts, and my answer was positive. So what does that tell me when my answer is positive? That I picked the right direction. So those directions are right. Now, I'm going to get rid of all this, and let's do KVL somewhere else. We could do the one that's all the way around the outside of the circuit out here. I'll call that loop 2. So our second KVL equation at loop 2, again, I'm going to start here at ground. And when I encounter that 20 volt source, that's a rise. So I'm going to say plus 20 and continue around along the outside here. Now, when I get to the 10 ohm, I don't know what direction that voltage drop is either. So I'm just going to pick a direction and call that V1. I'm just going to say that's a voltage drop and draw in my V1 and subtract it in my equation, minus V1. Continuing on, I encounter E3, which is going from plus to minus. That's a source. I can't change that. That is a drop in that direction. So that's minus 8. And then I get back to where I started, which prompts me to set everything equal to 0. And when I solve for V1, I move it to the other side, it becomes positive. I see that for KVL to be upheld, I need 12 volts drop across there. The voltage is positive, so I picked the right direction there too. I should probably pick a wrong direction just so you see that. But I guess we're just lucky that way. All right, so I'm going to get rid of all my loop drawing here. And now what do we have left? We have left the voltage drop across my 4 ohm resistor. So I could use this loop here or this loop here, and either one should give me the same voltage drop across there. We might even try both. So let's call this loop 3. So my third KVL equation. I'm just going to start here, travel around this way. That's a plus 5. Here is a minus 12, okay, because it's going in that clockwise direction. That's a drop. Continue along this loop here. Again, I don't know what direction that the voltage drop across R2 is going to be. Let's just assume it goes this way. So let's assume it's a voltage drop. Then I get back to where I started, so I set the whole thing equal to 0. And let's solve for V2. So when I move V2 to the other side, it becomes positive. And now look, I've got a negative 7 volts. So what that means is I do have a drop of 7 volts there, but it's in the opposite direction. So what I'm going to do is take away my directions and draw it in the other way. It's actually a drop in this direction. All right. Now, just to check, let's write an equation for this fourth loop. Just because in circuit analysis, often we can check our work by applying another tool or just going one step further. There's a lot of redundancy built into these circuits, and we can actually be pretty sure of our answers when we're done. So here, going in that clockwise direction, I see that I have a plus 15 there. I decided I found minus 7 across the 4 ohm resistor there. And then minus 8 equals 0. Does it? 15 minus 7 is 8, minus 8 is 0. So that actually worked. So that tells me that I found the right voltage there. Okay, so I've got all my voltages. But what about the currents? I don't know any of the currents, and I can't really use Ohm's law to find the current through a source. However, now I've got voltage drops across resistors, and that's going to help me find my current. So I'm going to have a current here. Now we're going to use our Ohm's law equations. So my current here would be the voltage drop across that resistor divided by my resistor, or 1.2 amps. What about through the 4 ohm resistor? I've got 7 volts across a 4 ohm resistor, so 7 divided by 4 would be 1 3/4, which is 1.75 amperes. And then what about the current through R3? Again, it's going to go in that downward direction from plus to minus, and I've got 15 volts divided by 5 ohms. So I must have 3 amps there, just using Ohm's law so far. And now we're going to use our KCL. So let's look at this node B, where we've got 3 amps leaving through R3, 1.75 leaving through R2. So we must have some current coming in from here because we have no current coming in anywhere else. And it must be 4.75 amps of current. Okay, if that's true, let's go on to this one. So we've got 1.75 amps coming in, our 1.2 amp coming in. So this current must be leaving, and it must be in the amount of 2.95 amperes. So what about over here? We've got 3 amps coming in. We've got 2.95 coming in this way. So we must have 5.95 amps leaving. And then that would be my current through coming from my source, my 20 volt source. So that same 5.95 amps would be here. And notice we've got 4.75 leaving this way, which leaves our 1.2 over on this right-hand side as well. Okay, so this was a little different. We couldn't do our reduce and return, but what we could do was use all of these tools that you've been learning so far, Ohm's law, KVL, and KCL, in some creative ways to find all of the voltages and all of the currents throughout the circuit.